This is homework 5, question 2. So question 2 asks fxy is equal to 1 over a y square x when y is larger and equal to 1 and x is larger than 1 over y and smaller than y. So sub-question 1 asks about draw the non-zero definition region of fxy. So we can see that we first draw the x-axis and y-axis, and because y is larger and equal to 1, so we draw a constant line at y equals to 1, and x is larger than 1 over y, so we draw a line that x is equal to 1 over y. So it is like this, and x is smaller than y, so we draw a line that x is equal to y, and we can see that it is like this shape. And when y is larger than 1, we have this shading area, and x is larger than 1 over y, so it is like this shading area, and x is smaller than y. X is smaller than y, so finally we got this area. This area is the non-zero region of fxy. And the subproblem 2 asks about find a so that fxy is a valid joint density function. So by definition, the fxy is a valid joint density function when the integral of fxy dx dy is equal to 1. So we can write, like, based on this, we can write the integral of so y's value, so it is larger than 1, so the lower base is 1 and to infinity, and the integral of x is, the lower base is 1 over y, and inside is 1 over a y square x dx, and outside is dy. So first integral inside, so we can get like moving this 1 over a y square outside, and then integral the 1 over x, so we can got ln x with a value of lower base 1 over y and upper base is y, and we got ln y minus ln 1 over y, so the ln 1 over y is equal to minus ln y, so this set is equal to 2 ln y, and outside integral of dy, we can get integral of lower base 1 upper base infinity 1 over a y square 2 ln y dy, we get 2 over a integral 1 infinity ln y divided by y squared dy, and we set a is equal to ln y and y is equal to e to the power of a, and this equation can change to 2 over a integral infinity to 1 a over e to the 2a ea dA, and this can write to as this, so it's a over e to the power of a dA, and it is equal to the integral infinity 0 to infinity a dE to the power of minus a. So this part is equal to a, so it is the same as this part equal to a to 1, sorry, so a is equal to 2. And for question 3, it asks find and draw the marginal density function fx and fy. So fx is equal to the integral of minus infinity to infinity fxy dy, and fy is the same, integral of minus infinity to infinity fxy dx. So because we know that the x region from 1 over y to y, so for the fy we can get like integral of 1 over y to y, and this is fx function 1 over 2 y squared x dx. So this one we get already from previous, that is long long x over 2y squared dx. So we can get, by integral this, we can get long y over y squared, and this is in range when y is larger than 1. So otherwise, when y is smaller than 1, it's gonna be 0. And for fx is equal to integral of minus infinity to infinity fxy dy. So y has a condition y is larger than 1, and x is equal less than 1 over y, and larger than 1 over y and less than y. So when x is in the region of 0 to 1, the fx is equal to integral of 1 over x to infinity and 1 over 2y squared x dy. So this is going to be a constant 1 over 2, and when x is in larger than 1, fx is going to be 1 over 2x squared. So this is subproblem 3. And for problem 4, verify fx and fy are valid density function. So fx is equal to 1 over 2 when x is in the region of 0 to 1, and 1 over 2x squared when x is larger than 1. So we're gonna integral these two parts. So first part, integral 0 to 1 1/2 dx, and plus the second part, integral 1 to infinity 1 over 2x squared. So it's gonna be 1 over 2 plus minus 1 over 2x from 1 to infinity. So we get 1 over 2 plus 1 over 2 is equal to 1. So yes, fx is a valid density function. And for fy, we're going to integral of 1 to infinity ln y divided by y squared dy. So we get previously is equal to 1. So yes, fy is a valid density function. And this is question 2.